In this example, we want to find the equivalent spring constant of the system if we are tracking the degree of freedom being the weight W at the end of the cable. Now, what makes this different than some of the previous examples we were looking at is we are going to allow the deformation of our objects. So we are going to account for the fact that the cable itself is deformable. It's going to be able to stretch as this weight is applied and move. And also this transverse beam with a length of B is also going to be able to deform under the loading. So as we start to make our model, we want to begin by kind of drawing the situation that we have here, and then we can keep simplifying it until we get one spring, one damper, one mass. In this case, there's no damping though. All right, so what are we really trying to find here is we want to know if this is going to be what we're tracking is this weight. I'm going to say that it is going to have a degree of freedom x positive down, just so we know what degree of freedom we're trying to track. And this weight is attached to the cable here, and the cable we are allowing to deform, and we're saying that the cable is going to act like a spring. So it's going to have its own K. And I'm going to call that K1. Right, so K1 will be the equivalent spring constant of the cable. And that cable is in turn attached to this hoist or this winch, and the winch is sitting on this beam, which is again a deformable object. So the beam is going to be able to move as well with its own spring constant, I will call K2. And then that beam is rigidly attached to the wall. It's cantilevered to the wall. So in modeling this, you'll notice that I modeled this as a spring being the cable connected in series to a spring that is this transverse beam. And the way we want to think of, are they going to be in series or parallel or something else, we can think about their independence of motion. So if I hold the hoist steady and don't allow it to move up and down vertically, can I still move the weight? In this case, yes, I can pull the weight up or down because it's still connected to the cable. The cable is allowed to stretch even if the beam it's connected to cannot. And then same idea, let's say that I don't allow the cable to stretch. Can I still move W up and down? Yes, because I could still push down on the winch, and that can move vertically, which would still move W relative to its equilibrium position of X. So since these springs can stretch independently of each other, we can model them in series. And eventually we want the simplified model to look like this, where we just have the one spring connected to this inertial frame. And then that is going to have some spring equivalent, spring constant K. So let's go about finding spring constants K1 and K2, and then we can further simplify it down to that single equivalent spring of our system, W. And once again, I'll point out that we are tracking our degree of freedom to be the vertical displacement of W, and that is going to determine K1 and K2, which are going to determine K. If I were tracking a different degree of freedom, I would be getting a different spring constant out of this. So let's look at K1 to start. Right, so that is going to be the spring constant of this cable. So where I can start with this is going back to EMAC 213, or strength of materials. I know that the cable is going to have this constant force in it, W, at least when we're in static equilibrium, which is how we are going to be deriving this. Now, when we get to real continuous systems later in topic 3, now the dynamics of all the points are going to become much more important. So we are certainly making simplifications when we are modeling our beams, our cables, and everything right now. We're assuming that we can model it as just a 1 degree of freedom system, even though they actually have an infinite number of degrees of freedom, which we'll get into later. So we'll derive this just like we would in strength of materials for right now. So if we're pulling down with W, the internal force in it the whole way through is going to be W. Now this cable we can treat as an axially loaded beam. Now it can only hold tension, so that's another thing that makes it a little bit different than a beam that could be hold tension or compression. But again, for simplicity, we're going to model it just like an axial beam. So we know that its deformation, I'll call delta, is generically PL over EA. So in this case, its delta, I'll call it delta 1 so that we don't confuse it later. So the deformation in the cable is going to be its internal load W times, and we are given L to be the length of the cable, at least in equilibrium position. We are told that both materials are going to have the same Young's modulus E, and then we need A, which will be the cross-sectional area of the cable. And we're told that the cable is going to have some diameter D. So we can write that. We know that the diameter squared over 4 times pi is going to be the area, the cross-sectional area of our cable. So I can rearrange this because I want K1. So K1 is going to be the ratio of the internal load to the amount of deflection in the cable. So I need to find W over delta 1. So if I rearrange the above expression, I'm going to get that pi d squared E over 4L is going to be the equivalent spring constant of just the cable. Okay, I can put that aside for the moment. I have the K1, but now I want to look at my K2. And I'll put them together to get my full equivalent spring constant later. All right, so K2 is this beam in transverse loading. So I'm applying this force W at the end of it, and the beam is going to have a length of B, it's going to have a thickness of T, and it's going to have a width of A, as we see from the right picture. So all these are going to come into play. Now this beam in transverse loading, we know that, I'll call it delta 2 here, is going to be equal to the WL cubed over 3EI. And we saw this from the beam table. We saw this from the previous example. It's the same situation. We have a cantilever on the left. We have a free end on the right. And we're applying a force all the way at the degree of freedom we're trying to track on the right. So again, if it was a different makeup, if it was like a pin-pin, we're going to need a different constitutive relationship for that. All right, so W we know. L is going to be B. So L here I'm using generically, but it's going to be B in this case because that's the length of this transverse beam. E is given to us. I we're going to need to figure out what that is. So let me rewrite this now. So it's going to be W over B cubed for the given parameters over 3E. And now I need to look at I. Right, so if we recall, when we have a beam in transverse bending, we need to look at how does the beam look from this viewpoint. So I'm looking down the beam here. So I know it has a thickness of T and it has a width of A. So this is what I'm going to need to use to calculate the proper area moment of inertia. Right, so I need the area moment of inertia that is going to be calculated based on a horizontal neutral axis because that is the axis I'm going to be bending about. So thinking back to strength and materials for this, that means that I'm going to need to use that, it's a rectangular cross section, so it's that 1/12 BH cubed generically. So in this case specifically, it's going to be 1/12 B is the linear parameter is always the one parallel to the neutral axis we are bending about. So actually that is going to be A in this case. And then the H cubed, the cubed parameter, is always the dimension perpendicular to the axis we're bending about. So the I in this case we want to use is AT cubed over 12. So I can put that into my calculation over here. And I can simplify this a little bit. I can put the 12 up top, and that's going to cancel with the 3. So I am going to be left with a 4WB cubed over EAT cubed. And I can rearrange this again because what I want out of this is that equivalent spring constant K2. That's going to be W over delta 2. And I can rearrange all of this. So I'm going to get EAT cubed over 4B cubed. Okay, so that is the equivalent spring constant of just that transverse beam. I have my K1 and my K2, and remember in my original diagram, they are in series. I need to do another simplification because I want to combine them into one equivalent spring, K, for my modeling step. So now I know that K, for springs in series, it's going to be the harmonic average of their values. So in this case, it's going to be 1 over K1 plus 1 over K2. And here I'm actually calculating, that's for K. So 1 over K1 plus 1 over K2 will be the harmonic average. So let's see what that's equal to. So I'll do this up in Mathematica so I don't have to do all this algebra by hand. So the K1 is going to be equal to this fraction that I'll input here. So from what I did before, that was pi times d squared e over 4L. All right, so notice I put EY here so it didn't think that it was that constant E, the 2.1828, because Mathematica will assume that otherwise automatically. Okay, so K1 appears to be in here correctly. K2, I have here, that was that EAT. So I'm calling EY A T cubed over 4B cubed. And that appears to be calculating that correctly as well. All right, so that's my K1, that's my K2. So now I want to put in my harmonic average. And again, I'll let Mathematica do the heavy lifting on this. So 1 over K1 plus, and then I need 1 over K2. All right, so it literally did that, but we can go further if I use the simplify command. And maybe even a little bit further with a full simplify. All right, so this is what I get in the end here with a full simplify. It put it all over as one fraction. And it's kind of a mess here, but it's still a little bit better than we could have generated by hand probably. So I can paste that in here so we can see what that looks like. And we get this simplified expression. I'll just rewrite it by hand. So we have this AD squared E pi T cubed over, really I can pull out a 4 from all of this that Mathematica didn't want to do. B cubed D squared pi plus AL T cubed. Right, so that is what we get for this T equivalent or K equivalent for this system. Right, so we have these two springs that we treated as being in series with each other. We individually found their equivalent spring constant because each was a deformable body. So we had to use the constitutive relationship for each to find their individual spring constants, then realize they were in series, and we can add two springs in series by taking their harmonic average. And here we used Mathematica to do the algebra for us. And in the end, we got our complete equivalent spring constant for our system if we were tracking the degree of freedom being the vertical displacement of the weight hanging down from the end of our system.